In the previous section, when we were discussing AVL trees, we mentioned that AVL tree keeps the tree balanced all the time. And also remember that if the tree is balanced, your worst case performance would be O log n, because that would be the depth of the tree. Now the worst case is O log n, which is true for the leaves. What if you want to access a node that is a leaf frequently, or maybe not specifically that node all the time, but that node and its neighbors, which are also at the leaves or very close to the leaves? So it would be like you're always working with the worst case performance. Also remember that you still have to deal with these rotations that keep the tree balanced. So in splay trees, we're going to actually deal with that idea. So you will remember this figure. We looked at similar figures. So it is possible that because of some biased input, we may be ending up with a degenerate tree like you see in this one. This looks more closer to a linked list rather than a tree. So if the worst case performance is ON, as we saw in the previous example, I could still tolerate it if that worst case performance occurs occasionally. Now note that this is not true in all cases. There might be some scenarios or some applications where you cannot tolerate worst case performance of ON, even if it rarely occurs. But there are also applications where it's not so critical. So as long as it happens once in a while, you can tolerate it. So we're looking at such applications. However, it is not uncommon that we see this bad performance, very frequently, especially in a sequence. Like earlier, your algorithm could be working fine, but then you hit an element which is very close to the very end of the tree. So you have a performance of ON for that node. Then you again try to access the same node once again, or maybe not exactly that node, but one of its neighbors, which is also all the way down the tree. So you will again have ON performance, and then ON performance, ON performance. So if you have such a sequence of M operations which cause ON performance, in total you will be experiencing OM times N, which is probably something that you cannot tolerate. So the splay trees actually deal with this. The basic idea is what we call principle of locality. That's a very commonly used term in computer science. It means if you are dealing with some node or item, the next thing you're going to be dealing with is probably something closely related or close by. In other words, a neighbor node. This is just like you can consider an example as follows. Let's say we're talking about a university system, a registration system in a university, in which a professor wants to retrieve some information about a student. Okay, so it will take some time to find the record for that student and bring it to the display of the professor. Then the professor wants to look at another student. Guess which student that would be. With a very high probability, the next student would be again a student who's taking the same course. It's not very likely that the professor first picks a student, say from computer engineering department, and the next student the professor is looking at could be, say, from the economics department. That's not very likely. Probably it is yet another student from the same class. So that means the professor would be interested in students that are in some proximity, that are in the same department. So probably their records are stored together. Okay, so this is what we call principle of locality. Once again, the principle is if you're dealing with an item, the next item you're dealing with is probably in a close proximity. It's not guaranteed, but this is probable. And that's what Splay tree is based on. It's based on principle of locality. It says, well, I might be experiencing some better performance the first time I try to access a node, but if I can do some operations which will reduce the cost for the follow-up operations, and I look at the overall cost of the whole set of operations. Now, although the first operation was expensive, since I made the follow-up operations cheaper, in total, the whole thing has become much cheaper. So that's the basic idea. So in the case of a Splay tree, if you're executing M operations, the first one might be more costly, but Splay tree guarantees that M operations in total will have M times log n time complexity. Of course, this works if our assumption on principle of locality holds. If the operations, if these M operations are completely unrelated, like the professor picks the first student from computer engineering, second from economics, the third one from chemistry, the fourth one from psychology, then I cannot relate these records. So each one could be uh, incurring a very high cost. Okay, so this works if the application works with the concept of principle of locality. That's actually why we're teaching you so many different algorithms, because there is no one size fits all solution. You should look at the problem in hand. You should understand the problem with all its dimensions. You should also know several different approaches and their pros and cons. Then you decide which algorithm to use. So I'm not saying that Splay tree is better or worse than AVL trees or for anything else. You should know all of these. So as you said, as long as the principle of locality holds in your problem, Splay tree guarantees that these M operations altogether will incur O M times log n time complexity. So we say the Splay tree has some amortized performance runtime of O log n per operation. Now, here it was for all M operations. This is the cost per operation. So this amortized runtime means the performance in the long run when you have a long sequence of operations. It doesn't say that each one will be log n. It says the average of them will be O log n. As I said, it does not preclude the possibility that some individual operation, especially probably the first one, will be causing some high worst case performance. Anyways, if any particular operation is On and we still have the amortized performance of O log n for the overall thing, this could be tolerated. If you now what we're going to do is we will do some operations, we will perform some rotations that will guarantee this. If we don't do those operations, those nodes will stay where they are. And each time you try to access them, it will still cause ON. So these rotations are actually providing the solution for accessing this, for having this amortized performance. So the basic idea is every time you access a node, you just take that node and pull it towards the root by doing some rotations, as very similar to the ones we did with AVL trees. And this sequence of operations, one after another, to bring the operation, sorry, to bring the node that you wanted to access, is called splaying. We say we're splaying that node. It means we're pulling that node from where it was all the way up to the root of the tree. If the node you're trying to splay is deep, then you have many nodes on the path to move, which will cause a significant restructuring of the tree. However, later in the follow-up operations, you will benefit from this. So it will be worth the cost. So look at these operations now. Now, these operations are very similar to what we did with AVL trees. So it will be very easy for you to understand it. So assume that we have the tree on the right. If I do a rotation, in this case a right rotation, for K1 around K2 this way, what happens will be we will take K2 and Z down, remember, K1 and X will go up. So K1 and X go up, K2 and Z go down, and Y gets inherited by K2. This is just the right rotation we had with AVL trees. Now, the tree we had before the rotation, the one on the left, was an AVL tree. We know that. I'm sorry, the one on the tree was a binary search tree. Let me correct it, not an AVL tree. It's a binary tree. Now, how about the one on the right? Is it still a binary search tree or not? How do we guarantee that it's still a binary search tree? Well, it's actually straightforward. If the one on the left was a binary search tree, that meant anything in Z was greater than K2. K1 was less than K2 because it's the left child. Anything in S is less than K1 because, again, it's the left child. But K1 was smaller than K2, so that means X is also less than K2. How about Y? We know Y is greater than K1 but less than K2. So we can say anything between K1 and K2 is in Y. Anything greater than K2 is in Z. And anything that's less than K1, which also means it's less than K2, is in X. Now, after we do the rotations, that should still be true if this is a binary search tree. Well, anything in S should be less than K1, which is same. Anything in Z is greater than K2. That's also the same. Here, K1 was less than K2. Here, K2 is greater than K1, so it's the same thing. And anything in Y is between K1, they're greater than K1, but less than K2. It's between K1 and K2, which is also same here. So we have not changed the orders actually. We did the rotation, but still we're preserving the binary search tree behavior. So that's good. So this kind of rotation is something that we can use. So when you're trying to splay a node, which remember means pulling that node all the way to the root, you need to do some rotations. So what we're doing is we're taking that node and applying a series of rotations for X until it becomes the root. So I'm not saying one or two rotations. Do necessary rotations until it becomes the root. It might require many rotations. So How does it work? For each rotation, what you do is you first check if x is root or not. If x is root, we're done and we terminate the algorithm. If not, it is possible that x is not the root, but it's a child of the root. In that case, it has no grandparent because its parent is the root, so there's no grandparent. So if x is a child of the root, then just rotate x about its parent. In the next iteration, you will hit the first case. Now x has become the root when it is rotated about the parent, which is the root. It will stop in the next iteration, but at the moment, we just rotate it about the parent, which is the root. Now, for other cases, which means x is in level 2, remember level 0 is the root, level 1 is the children of the root. So if x is grandchildren of the root, or maybe even down, in that case, there are two possibilities. Either x and its parent, its immediate parent, they're both left children of their parents. So that means parent of x is a left child of the grandparent, and x is also left child of the parent. Or maybe they're both right children. In that case, you rotate the parent of x, around the grandparent, okay? And when you do that, the parent of x becomes now, it moves to the upper layer, pulling also x up. And then you rotate x about its parent, which means x goes one level up, taking its parent down. So in two rotations, you will get x raised by two levels. Or the other condition is x and its parent are opposite type children. That means one is the left child of its parent and the other one is the right child. In that case, it's not important whether it's left, right, in the order left, right, or in the order right, left. The important thing is they should be different types. In that case, you rotate x about its parent, which means x gets raised by one level. Then x about its new parent, which was the earlier grandparent. So x gets promoted. Once again in two rotations, x moves up by two positions, two levels. So let's look at some example. Let me just zoom in so it becomes more readable. Okay, so let's look at this generic case. In this case, x has no grandparent, so it's the child of the root. P is the parent of x and also happens to be the root here. So remember, you just rotate x about its parent, which is the root. So x goes up, P and C go down, as we see in here, and B gets adopted by the new node that comes here, which happens to be P, as you see in here. Now that one's easy. When x and its parent are the same side, then you do the following. This is called what we call the zigzag style. Zigzag means they're both the same. Zig and zig, they're the same. So it's left, left, or right, right. Okay, like if you look at here, x is the left child of P, which is the left child of G. Okay, so that's why we call zigzag. So the first thing you do is you don't rotate x immediately. You first rotate its parent around the grandparent. So G and D go down, as you see in here. P goes up, pulling x and A also up, x, A, and B up. And while P was going up, its right child C gets adopted by the node that comes in here, which happens to be the former grandparent. So C is adopted by G. We know how to do this, as I said, from the AVL trees. Now that was the first step. In the second step, this time you rotate x about its parent on this updated 3. Okay, so P will go down, pushing G, C, and D down, as you see in here. X goes up, pulling A up, and B gets adopted by the new node that comes here, which happens to be P. So you end up with this tree. Note that X has moved 2 levels up. Here it was at level 2, now it's in level 0. Note that this example is a generic example. So G doesn't always have to be the root. It could be somewhere in the tree, and you should keep on repeating this until X becomes the root. In our case, X has just become the root, so we stop. Sorry. Now the next case is what we call the zigzag case. This time the node and the parent are on different sides. So note here the parent is a left child, but X is a right child. So we have a left-right operation here. It could also have been the other way. It could be right-left, doesn't matter. It's the same thing. So the solution this time is you rotate first X around P. So X will go up together with C, A and P will go down, and B will be adopted, as you see in here. Now what I did is I brought X to the left child of the grandparent. So now I can rotate right. So G and D go down, X, A and P go up together with B, and C gets adopted by the new node that comes here, which is G. And that's what we see in here. So once again, this was a zigzag case where both X and its parent are same type of children, and the other one was for the case where they were different types of children. So the operations that we need to perform are insert and find, or contains, however you call it. So in the case of insertion, you first put that new node to where it should have been, just as you do with regular binary search trees. After you do the insertion, then you apply the Splay operations, very similar to AVL trees. In the AVL tree case also, we first inserted, then did the rotations. So same in here. First insert, then start splaying that new node that you inserted. Why? Well, I just added this into the database, for example. Probably I will need either this item or something that's close by in the follow-up operations, because it seems like I'm interested in this vicinity, in the nodes that are somewhere around here in this neighborhood. Now, if when you're doing an insertion, if this insertion causes a duplicate, in that case, you don't splay the node you just inserted, but instead you splay its duplicate. Why? Now the idea is, if you have inserted this one, you're already done with this, so probably you will need to look at the one that's similar. You could have done it this way or not, but the algorithm works this way. In the case of a find operation, you just do the search again as in the binary search trees. Remember, anything smaller is on the left, otherwise it's on the right. When you find it, you splay it. That means you search for that element. You took all the cost of going all the way down to that position. But once you find it, let's bring it to the root, because in the next, for example, find operation, probably I will again be searching for either the same item or an item that's close by, again, according to the principle of locality. However, what you're searching for, maybe you couldn't find it. If that happens, if you cannot find what you're searching for, this time you don't splay what you inserted, but you splay the last node you accessed while searching for that element, which is one of its neighbors. If it were there, it would be a close by neighbor, so you splay that one. For the case of remove operations, it's a little bit more tricky, but again, it's very similar to what we discussed in AVL trees. The splay element you first find the element to be removed. You splay that element first before removing it. You bring it to the root. Now, if the element to be deleted is not in the tree, like you want to delete something, but actually it doesn't exist in the tree, maybe in the database. So again, like what we did in the search case, because actually to be able to remove, you first try to find and then you remove it. So while doing that search operation, the last one you visited, since although you couldn't remove anything, at least you splay that one and you would be done with the remove algorithm. But if not, if what you want to remove is there, you first splay it. Now you're going to remove it. Now remember, when you splay it, you bring it to the root. Now you're removing the root. When you remove the root, you will be left with two subtrees. One is the what we call TL tree left. It's a left subtree of the root, and TR is the right subtree of the root. You end up with two subtrees. Now you need to merge them under a new root because it has to be a single tree. But if each one has two children, you cannot merge them. You cannot put one under the other because in that case it would be three elements, sorry, three children. It would have to have three children. So what you do is you splay the maximum in the left subtree. Remember, the left subtree is a set of elements that are smaller than the root. So among those that are smaller than the root, you find the maximum one, which means it's the closest one to the root, but still smaller than the root. You do just the inverse in the right subtree. And this way, you will have actually two subtrees where their respective roots do not have the left or right nodes. Because in one, it is the largest element, so everything means it means everything is smaller than that, so it doesn't have any right children. In the other one, you found the minimum element, the smallest one, so everything would have been larger, therefore it wouldn't have any left node. Now those could be easily merged together. So you connect them depending on which one you're connecting to the other. One would have an empty child and it would be attached there. So let's look at some examples. In this tree, we want to find 65. Well, you know how to do it in binary search tree, so you simply go 65 is larger than 50, so you go right. Larger than 60, go right. Less than 70, go left. Oh, here it is. Okay, we found it. Now, in the case of a binary search tree, we would stop here. In the case of a splay tree, now we start rotating, splaying actually. How do we do splaying? I should be splaying 65. Okay, so first I would rotate in this way. So 65 would come here, 70 would go down. Here I would have 65. And as 65 goes up, 63 would also go up. So here I would have 63. And this node would be gone. It has been moved up. And 66 is adopted by 70. So is this a binary search tree? Let's see. Anything below 60 is still greater than 60. Here we have 65. If what you're searching for is less than 65, you go here. If it's larger, you go here. 66 is larger than 65, so you go this way. Remember, we have removed this link, so you go this way to the right. Less than 70, so you go left, and there you find 66. So it works. Now, this is the updated tree. Now, you're going to do the second operation, second rotation operation. So this time you splay 65. We're still trying to splay 65, remember, because we're searching for 65. So 65 will go up, okay, and 50 will go down. So it will be like 60 comes here, 50 goes down here, therefore 40 comes here, 20 comes here, and here will be 16. And as 40 goes down, also 43 comes here, so it's not here anymore, okay? And 60 has moved up the root, so this will be 65. Remember, the right child of 65 is now 70, and its left child is 66. So now here we have 66, and these have gone up. And now 65 is here. So do the rotation once again. 65 goes up. Here we have 60, 60, 50, 40. This will go down once again, one level. And the 70 here will also go up one level. So 65 will come to the root, and I would be done. That would be the end of the algorithm. So for the remove operation, this time we're trying to remove 25 from here. You will just first splay 25, so bring it to the root, and then remove it. But when you're trying to remove it, find the largest in the subtree, and then splay that value. Do just the inverse in the right subtree, then merge them together. Just try it yourself. I will not go over that. Now, when you're trying to insert an element into the right subtree, into a splay tree, remember that in a binary search tree, building a tree from n-sorted elements had the complexity of O(n) squared. Now, what if we use a splay tree rather than a regular or ordinary binary search tree? So, for example, assume we had an initially empty tree and we want to insert the value 1. So we insert 1. Now, we're talking about sorted elements, sorted input. So it's a kind of biased input. So the next element would be 2. So you first add 2 to the right child of 1. But then, remember, in the case of a splay tree, we splay what we have inserted. So after insertion, after you have this small tree, so let me just zoom in more. So once you insert 2 to the right of 1, you immediately do a splaying operation for 2. So 2 goes up. So 1 will be the left child of 2. So you will end up with this. So this will be the final splay tree after the insertion of 2. Now you have this element and you try to insert 3. 3 will come to the right of 2. So that's what we have here. And immediately splay 3. So 3 will go up to the root. Then you will have this. So it works this way. You insert 4, and it's what you will have. Now, in this tree, assume that you try to access 1. You will go 4, 3, 2, 1. When you find 1, you will splay it, and when you splay it, you will have this snake-like tree structure when you access the value 1. So as you can see, the splay tree is also very close to getting sometimes degenerated, or at least having very strange shapes. Actually, for example, if you look at this tree on the left, assume this is your original tree. Now, see how much a splay operation might change the shape of the tree. Let me just zoom in a little bit. Assume that while given this original tree, we try to access node X. Pay attention, I'm not adding or removing any elements, just trying to access x. I will find x, and once I find x, I will need to splay it, which means bring it to the root. And when you do the splay operation on x, you end up with this tree. Now look at the shape of this tree on the left, and look at the shape of this tree on the right. Without doing any insertions or removals, the tree significantly changes its shape. When you're doing a splay operation, we say we're doing the splay operation up the tree as we're going to the root. Now, how do we traverse up the tree? How do we go up? What I mean is the following. Okay, I know how to go down to find x, but once I find x, now I need to do some rotations. So I need to know who the parent of x is. Normally, our links are working from parent to child. They're directional in one direction. Now, how do I find the parent? It's easy to find your left or right child, but how do you find the parent? Actually, there is no link for this. What you can do is you can add a new link to the data structure for each node, but that would require that you have more overhead now because you add one more link to each node. So that's one thing. The other thing is, okay, I found the parent with this additional link. How do I know if I was the left child or the right child of my parent? I found my parent, but from the point of view of the parent, am I left or right? That's another question. So now it would be like you first go up to your parent and then try to come back to yourself to see if you're left or right child. That would be again some additional operation, so it would be costly. How do I know if X is a grandparent? You first try to go to your parent and then try to go to its parent. So all these have advantages and disadvantages. There is actually a solution for this. We will not go into the details of this, but rather than trying to write the code that goes up and down the tree as we have discussed, so one solution would be having those links. It is possible to design the Splay tree only in one direction, top down, and you start from the root rather than the node X you have found, and on the way down you're doing rotations as necessary, and the tree is split into now 3 parts depending on the path you're trying to access, you're using to access. So it's either zigzag, or zigzag, depending on whether X is the current node that's being accessed or you're trying to go to its left or right. And as you go down the tree, you have X, left, and right, 3 parts. The node you're at, its left subtree, and its right subtree. And as you're going down, you're doing reassembly. This method is faster in practice and uses only O1 extra space because you temporarily have to store these 3 components. Since it's fixed, it's O1, and still is able to achieve O log n for amortized runtime.